everyone. We have an incredible guest today. Nicole Königstein is joining us. Nicole and I met actually through our mutual employer and O'Reilly. She's recently written chapters for 2 books on AI and is in progress of getting her PhD as well as teaching courses for O'Reilly. So I'm really excited to have this conversation with you, Nicole. Tell us more about yourself.
Yeah, first off, thanks for having me, Vicky, and thanks for a nice introduction. I think I can't add much more to that.
You're very humble. You're doing so much at the same time. You've already published a book on transformers and really abstracting a lot of the AI concepts. And I would love for you to maybe dive deeper into that methodology and how you think about transformers and improvement in multimodal interactions.
Yeah, sure. So, I actually started out using transformers like back in 2000, quite a bit back. So not jumping on the bus or the bandwagon when all did. And about 2 years later, I developed with attention my own architecture and started already teaching about vision transformers back then. And kind of what then came out of that was kind of a fascination that they are so versatile. So it doesn't matter if you have like language or any other modality. Mm-hmm. So it's kind of once you understand how transformers work, then you see really patterns to begin to emerge and you understand the deeper functionality and how they kind of process the different modalities. And yeah, what happened to me was that I kind of saw the same principles happening across images and then audio, video, time series, reinforcement learning, which is also just all coming down that it's a sequence. So you break it down to a sequence. And as soon as you understand that everything can be broken down to a sequence, you just have to adjust how you do it. So you have with images, you have patches. With audio, you have also patches. With video, you had it previously with older models a little bit different, but now you also have just those patches, and then you have that sequence, and the transformers can process that.
Pretty amazing. And you abstract a lot of the ideas. I think you have a way of just thinking about concepts. I know you're working on your PhD right now that revolves around self-improvement. And self-improvement is something we do as humans, is trying to improve ourselves and get better. Is that different to do self-improvement for humans versus AI agents?
The very interesting thing is, it's interesting that you ask that. So when I'm teaching about self-improvement or reinforcement learning for agents or transformer models, I always bring the example that everyone knows that already, how this works, because it's not that much different between how we actually learn and humans learn, because you have that reinforcement, right? Reinforcement learning, and yourself learn from positive and negative experiences. And transformers or AI agents, it's just the same. So even a bad outcome, then they fail their trajectory in finding a solution or fulfilling a task. They still learn from that as much as we do, and as much as we do also from something successful.
Interesting. And is there iterations? Like as humans, we kind of like pick a self-improvement topic. We want to lose 5 pounds, for example, and we start eating less carbs, and then, we take off some of the weight, and then tomorrow we gain 10 pounds back because we went back to eating bread every day. How does it work in terms of AI models? Do agents set those kind of self-improvement goals and then try to achieve them or fail at them, or is that the same?
Let me abstract this a little bit funny away, what you just said, because what you said, I would classify what you just said in terms of AI or AI agents or transformer models or LLMs. I would classify this as test time compute. So you're just optimizing for the current stream, for that current goal, if you're just wanting to lose 5 pounds or something.
Right.
But you're not updating this is now funny, but funny punch, you're not updating your weight in that sense.
Yeah.
which means the weight of your large language model or of your agent. And then if you really do reinforcement learning, then you update the weight, the model weight, and then you persist that learning. So this
Okay.
is different. And so this is just why I
So the
jumped in.
machines don't
So
go back and gain 10 pounds after losing 5.
exactly. If you change that behavior because of health, you really want to just not just for having it's bikini season and or
Right.
you're going to Hawaii or whatever
Yeah.
holiday destination and you just want to drop it. But if you have a deeper goal for that, so you really want to update your mental policy of how you approach that your health, then you really update constantly your weight, right? So you lose it and you stay at that level. And yeah, it's the same with LLMs. So if
Right.
you want that it sticks, you use reinforcement learning and you update the weight of the models.
And that's, I feel like it's easier for LLMs than it is for us, because once you update it, they kind of stay at that weight, right? Or that reinforced learning, and they just go from there. I know a lot of times when I ask ChatGPT about maybe a problem I'm having, the answer is you're only human. And that kind of classifies a lot of things, I feel like, with AI agents, right?
No, not necessarily, because there's still different parts. So with AI agents, there's not only that you have that policy and you update it, there are different things coming in. So I'm sure you heard about context engineering, right? So this is all what goes into your AI agents or in your models. There can be different sources, and also memory plays an important part. And you have episodic memory, you have procedural memory, and you have semantic memory. And all of that steers in. And this means you could or you can instruct, and you can do this with ChatGPT as well, that you want its reply in a certain way. So that's the procedure part. So you want all arguments in bullet points, or you're
Okay.
not, or you want whatever the reply in British English instead of American English, or whatever. And this goes into the procedural memory. So even though you might update it in a certain way, the weights of your model, underlying model for your agent, it still can behave differently. Also going to what you said with the weight, it still can diverge from what was it was originally like trained or taught to do.
Let's talk about that divergence, because that's probably one thing that most people talk about on businesses concern, is this non-predictive way that LLMs run, right? We can expect a certain outcome and maybe it gives it to us 90% of the time, but that 10%, it goes rogue and produces something completely different. I know models are getting better every day, so that rate of hallucination is decreasing, but is there a way, as it becomes more agentic and starts making decisions on its own, that we can control, not control, but at least have visibility into how it's making decisions and what outcome it's actually going to produce?
So with agents, there's another complexity which I think many companies or people are not thinking thoroughly about, which means that originally, before all the hype about AI agents, and we were just using sort of a monolithic structure, so one model, there was that like, all right, so if it's not working properly, we just go bigger and then it's better because we have more parameters and we get better system. Well, the problem is with agents, that's not working, because the problem is that if you add more agents, you add more failures, or you can add more failures. The problem is that we shift the task or the view of the problem from can the model solve this task to can the system really execute a stable sequence of decisions, because you wire different models, different agents together.
Yeah.
And that actually adds complexity. And this is about from 1960s or so, and it's called the product reliability.
Mhm.
And it just basically states that if you wire different components together, then this multiplies the failure mode. So if you have one weak model or one weak agent and then it gets to the next one, you have that error propagation, which eventually means if you have, or if you start with an success rate of one agent with 98% per agent, like if it's really a good one, all of that. And then you have for one agent, you have also your system accuracy at 98%. But if you then have three agents, for instance, still your per agent 98% accuracy, you have already an error rate about 6% because you're wiring it together sequentially. If you go to 10 agents, you can end up as high as 18% of failure because you're wiring them together. And if you don't control the error propagation throughout the system, well, then you
You have a
just
high error
propagate it
rate.
throughout.
Oh my
Yes.
goodness. I love that bring that up because people talk about agents, but they don't talk to them in terms of systems. And, I've heard people talk about creating agents and using the right model for the agent, but the propagation of error rate is something that hasn't really been discussed, at least on
Yeah.
this podcast. So this is super, super interesting to me because as the complexity increases, to be honest, companies invest more in AI, and they have to replace their processes. They will have to start stitching together agents more and more to essentially replicate their processes in the company, right? Or even in the factories around robotics, there's multiple agents that run those factories, and their error rate, yeah, is
Yeah,
important.
and yes, and thinking about what you just said, so there are two things. So for me and my mental model, and this is how I approach everything. So I'm really a systems thinker. So I need to model out and map everything, and then I do understand it. So for me, AI agents are just distributed state machines because they have a state and they follow that state, and you can track this state and you can make this like visible and traceable. And then they are distributed and they work on that kind of distributed mindset and fulfill the task. But the importance is how you stitch them together because you have different topologies. So there are like centralized multi-agent systems where you have kind of an orchestrator. So this is very much like you have with a human team. So you have that kind of a team lead, and then you have your team members, and that one instructs and the other work and then report back. And this goes to just the supervisor architecture, so just the team lead and then some sub agents. Or you can have it more complex, meaning hierarchical. So you have many supervisors with agents and then kind of a higher supervisor coordinating all those different supervisors. So kind of that, I don't know, that the higher of a team lead in that overall company or system. But this is just one topology you can have. There's also decentralized multi-agent systems. They are more collaborating together. So they fan out, and it's kind of the same as you know from nature with ants, birds, bees. So they work in swarms and they fan out, they find solutions and then come back, and then it gets kind of summarized and composed and put together as a final result. So you have also like independent, you have those different kind of parts, or then in hybrid where you kind of get the best of different worlds
Yeah.
together. And this is, I think this will be the hard part, because you need to start, if you are a company or a business, you need to start to think about how you map your business problem or existing business model into the right architecture, because not every use case fits the same topology. So
Yeah.
there are just some which are better for a certain part. So for instance, if you have it more organized and distributed, so the supervisor architecture is good. But for more deeper research, you might go with the swarms because they can then get different inputs and fan out and gather a lot of information in parallel. And then you just summarize it and get your information. You still have then maybe that hybrid, so meaning a planner, which then compounds what was found into something coherent and maybe have one refactoring and things between. So you get that kind of feedback loop. But yeah, that's, I think, one of the challenges among that you
Yeah.
need to think about this
One of
properly.
the things that I hear a lot from CTOs, right, is like, oh, we just released AI into the wild and everyone's using up all their tokens and my cost is for the roof because I didn't put any
Yes.
guardrails in place. So you can imagine these orchestrated or swarms of agents just going out and gathering information, but they're not thinking about cost and implications of that. Are there ways to put these boundaries or governance in place around these types of architectures?
Yes, definitely. And in fact, I'm writing one of my chapters going in that direction for the AI agents book. So everyone who has problems, please look into that. But no, yeah, definitely. So one of the things, and I think like you pretty well covered what's going on right now. People are moving from the happy sunshine PowerPoint presentation agent to production.
Exactly.
And there goes the big awakening. And
Yeah.
what is happening is you have one part is you have latency amplification, you have token cost explosion, and one of the problems what people might expect yeah kind of surface or what happens is that you have those retry loops. So meaning if something wasn't successful and then you just try again, eventually
Mhm.
it will succeed.
Right.
But the problem is those retries compound. So meaning if you want to get a higher success rate for a weak component in your system,
Yeah.
you need many retries. So meaning you can actually do the math and say, all right, so I have that base success, have a number of iterations of retries,
Yeah.
and then the effective success of that retree. Meaning if for instance your base success is just 30%, so 0.3,
Hmm.
and you want that what I was mentioning earlier, the 98 percent of success rate of effective one, you need 11 attempts to get there mathematically.
Yeah.
Like that's a lot, right? And if you don't have one agent, but let's say five,
Right.
then you have not one client using it, but tens of thousands. Yeah,
It
you spend a
multiplies
lot of
very
token.
quickly. Yeah.
Yes, it
And
gets
people
very
always say
expensive.
it's the same with humans, right? We always like, oh, just put another body on the project if you need to make it faster. And what happens is this person doesn't have
No,
the subject matter and they end up with a lot of retries. Oh, this didn't work, this didn't work. And so
yeah.
you end up actually taking longer in the project. And the complexity just increases by adding this person instead of decreasing and making it more efficient, right?
Exactly. And you can map this even more to also what I mentioned with that latency problem, because the problem also with those retries, it costs you time, right? So because the model tries again. And this means in production, because your user experience is defined by what's called tail latency. So meaning the amount of users getting that amount of speed.
Mm,
And if you have that latency, you have usually you decide about P95 or P99, so that 95% or 99% of your users get that high speed. But if you end up with P95 because of those retries,
yeah.
this means that out of one user from 20, the system feels broken because it takes too long.
Yeah.
And then you have that spiral that you don't just spend a lot of money, but your clients are unhappy because wait.
Because they're not getting what they need. And with Akamai, my current company, we talk about distributed servers because what we're your scalability issue. Now, especially when we look at factories and where the initial that output has to be quick and accurate, right? Otherwise, your production line slows down and there's a higher error rate, as we
Yes.
mentioned. It's super critical. How do you manage that? How do you govern that? And that's the number one question that I hear is, great, so we have this. So how do we manage it now? Because I can't scale the way I want to. It's costing me a lot of money to do that. Like, what is the right solution? And not everyone has
So,
the answer. Maybe you have the answer. Tell me.
well, I can point people in the right direction. So, one point is how you get from that kind of stochastic hope you're currently having with agents and LLMs and all of that is breaking that error loop. So, meaning if you adding that you're enforcing the schema that you have, so you have hands of the communication between agents and using tools and all of that, this goes via hands-off, right? So if you control that part, that part is accurate, that there is no gibberish, no wrong format. So if you need JSON and specific parts of JSON, specific, let's say, int instead of float, all of that, if you control that at that boundary level, and when it gets out of one model and one agent to the next, then you already break that error loop. This already increases your overall success rate.
Okay.
Then you can also, for instance, you can do this with LangGraph. So I'm using LangGraph because I can go low level with developing my agents, and also like using instructor and frameworks and Pydantic like that. And there you can orchestrate it in such a way that for the retries I was just saying, you can give information about the failure mode, what happened, back to the retree so that the model, the agent gets the information how to improve itself and just don't end up in that 11 attempts to get better. Maybe it costs just one or two because you got it the precise information what went wrong, how to correct it, and then it can correct it. These are already things you can do. Also, another thing is memorization, meaning that you don't have to recompute and redo all from scratch. So what I mentioned with those swarms, so if you send them out and maybe something, what they are looking up is semantically fairly similar to what another agent already found. So you don't have to go down that rabbit hole. You can store this in sort of a memory and use this, compare it semantically,
Yeah.
and do the
And
similarity.
improve the design with time because now you're keeping track of the errors and the frequency with which they're occurring. It's kind of like a log file for agents, right? Systems log file. Okay. I love that idea. That's super helpful because I didn't know how to address that question, especially like in the factory robotic settings where the response has to be so immediate and you don't have that retry situation. You don't want to wait 10 retries because your whole factory is going to just be out of
Of
service for
course
a
not.
while. Yeah. um so that's super interesting. I've learned so much from you, Nicole. Where can people find you and connect with you? Where can they read more? Tell me.
I think the easiest way is via LinkedIn to reach out.
Okay.
Yeah, they find me definitely there via O'Reilly, of course, but there it's harder to reach out personally. But yeah, LinkedIn is the easiest way.
Thank you so much. I just sent the connection as well because I realized we weren't directly connected. We were just connected through the Nicole at O'Reilly, but it's nice to speak with you today. And I hope you have a wonderful day. Thank you so much for this information.
Thank you, Vicky, as well.
Thank you.